Hello. So today we will still be doing something about the derivative of vector functions. If you remember, if we have a function of a single variable, suppose you are having something like this, ut, it is a function of a single variable, then the derivative, it's written like this. Okay, it's written as u dash t, or sometimes it's written as du dt or u dash t. We can express this one in terms of the limit. So you can write it as limit h tends to 0 upon h. We can write it like this, t plus h minus u bar t. Okay, this works for any point t. Okay, suppose if you are having for the point t naught, then t naught over here t naught plus h minus u bar t naught. If you remember, in the definition, instead of u, I was writing it in terms of f. So it will be f t plus h minus ft. Okay, but this symbol that we are having, it will just be a notation. In fact, we can use any vector. We can even use v, we can use f, we can use g. It doesn't really matter. What matters is this definition in terms of the limits. Okay, so today what we will do, okay, we have also seen the rules of the derivatives, but today we will be using three theorems. Okay, we will be proving them. It is something that concerns with constant vectors, vectors of constant magnitude, and vectors of constant direction. Okay, so let us just see the first theorem. This one is about constant vectors in general. Okay, the theorem, it states that theorem 1, a vector u is constant, or vector ut is constant if and only if ddt of u bar is equal to the zero vector. Okay, so let us try to prove this one. You will see that it's very simple. So there are two parts. Proof. We can prove the direct way. The direct way will be let u bar t be constant. So we need to prove du dt equal to 0. Okay, so since ut it is a constant, so what we can write is something like this. Since u bar t is constant, so u bar t, you will be having that this vector, it will no longer be dependent on t. So we can write it maybe as a bar, where a bar is constant. Okay, just let me use an example of what you know. Okay, so this one, if you are having something like this, fx equal x squared, it is not a constant function, because if you change the value of x, the value of fx will also change. That is, f1 you will be getting 1, f2 you are getting 4. So if you change the value of x, this expression will also change. Okay, so this one is not constant. Whereas if you are having something like this, fx equal 2 maybe, which is constant, then even if you put f1, it will still be equal to 2. If you put f2, it will be equal to 2. If you put anything inside the bracket, if fx equal to 2, then ft, it will also be equal to 2. It won't matter, because it is a constant function. Even if you have ft plus h or anything inside over here, if you change it, it won't matter, because it is a constant function. Okay, so keep that in mind. So now what we will do, we can just evaluate du dt in terms of limits. You can write it as limit h tends to 0 u t plus h minus u bar t upon h. Just like what I had explained, because it is a constant function and this one is a, so u t plus h, it will also be a. It won't matter. u bar t will also be equal to a upon h. So this one, a minus a will give you 0 vector. So the whole thing will become a zero vector. Okay, so we have done it. If it is constant, then du dt will be equal to 0. Okay, now the converse. The converse will be that du dt equal to 0. So we need to show that u bar t is constant. If you remember, any vector function can be written like this. Any vector function ft can be written as f1t plus I plus f2 tj plus f3 tk, where f1, f2, and f3 they are scalar functions. Okay, applies. Okay, now ut, it can be written as u1i plus u2j plus u3k. Okay, so we can write it like this, where u1, u2, u3 are scalar functions of t. So we take the derivatives of both sides. So du dt. Over here, some of you may be confused. Where does this t go? Okay. Actually, this one, it is just a notation to denote that u, it is dependent on the vector t. Okay, so we can easily write this one simply as u. Also, it won't matter if you mention somewhere else that it depends on t. Okay, but okay, let us write it like this. Du dt will be du1 dti plus du2 dtj plus du3 dtk. But du dt, it's equal to 0 because we have assumed that. So we'll be having this. Okay, so this is what we are having. So now what will we do? So ultimately we will be having that this one should be equal to 0. This one will be equal to 0. du3 dt will also be equal to 0. We compare both sides. du1 dt will be equal to 0. du2 dt will also be equal to 0. And du3 dt will also be equal to 0. So over here what we can have is that, because now they are scalar functions, and you have learned that if they are scalar functions, whenever the derivative is 0, then that function should be constant, u1. So similarly, u2 will be constant and u3 will be constants. Constants, scalar, constant scalar functions. So this is what we are having. Therefore u bar, because if you remember, therefore u bar, which is written like this. Okay, so this is what we are meaning. What we mean to say. If u1, u2, u3 are constant, so this vector will also be constant, because this u1 will no longer depend on t, u2 will no longer depend on t because it is constant, and u3, it is also constant, it won't depend on t. So this whole thing, it won't depend on t, is independent of t. So it is constant. So this is what we want to do. Okay, so we are done with theorem number 1. Okay, now let us do theorem number 2. Okay, theorem number 2 states, the statement is this. U bar t, again, okay, this one, it is just a notation. Okay, u bar t, or simply you can write it as u bar is of constant magnitude if and only if magnitude if and only if u dot du dt equal to 0. Notice over here it won't be 0 bar because it is a dot product. The dot product should be a scalar. That's why it will only be 0. Proof. So what we will do is, you must first remember the terms. Constant magnitude. Constant magnitude, it means that magnitude u, it won't be depending on t. Okay? It won't be depending on t. That is what we know. Okay, so the proof, you will first have to remember this line. U dot u. Just remember that u is no ordinary, it is not an ordinary vector. It depends on t. Okay, but for simplicity, we can write it as simply as u. Just remember that u, it is depending on the scalar t. Okay, u dot u, you can write it as magnitude u squared. You are noticing over here we did the derivative, so we can differentiate both sides with respect to t. So you will be having ddt magnitude u squared. If you differentiate this one, you can use the formula for the dot product derivatives. So you'll be having something like this, plus du dt dot u. Differentiation of this one, you will be having 2 magnitude u du dt. Okay, if you remember d dx of z squared, you will be having 2z dz dx. Okay, so similarly over here, okay, this is what we are using. Okay, because this one, it is a scalar function. Okay, so that's why we can use all the things that we know when we were doing functions of real numbers in lower classes. Now this one and this one, they are the same. Okay, because the dot product is commutative. You can write u to the front or u at the back for dot product. It doesn't really matter. Okay, you can interchange the order. Okay, so if you interchange them and then you can add, you'll be having this. Okay, so we will be having this. So what we can do, we can also cancel 2. Okay, and we will name this one as 1. Okay, this starting point, it will be the same for the direct way and for the converse as well. Because over here we are noticing if and only if, so there will be a direct way as well as converse. But this portion, it works for anything. Okay, so now we will prove the direct way. Let u bar t be of constant magnitude. So if it is of constant magnitude, so we need to prove u dot du dt equal 0. Okay, but now, okay, this one you can write it or you can eliminate it. Okay, it depends on you. So that's why I'm just writing it inside a square box. U bar is of constant magnitude. So this one, it will be constant. It's a constant scalar function. Okay, it is a constant scalar function. It is a scalar because it is the magnitude. And if it is a constant, so what will we be having? So this one, it will be equal to 0. So substituting in equation 1, substitution in equation 1, so over here we will be getting 0. So that is why the left hand side we will get 0. U dot du dt equal to 0. substitute this one equal to 0, so that's why the left hand side it will be equal to 0. So this is what we do. Okay, so this equation 1, as you can see, it's very important, so that's why it works for both ways. Okay, now the converse will be let u dot du dt equal to 0. The converse will be let u dot du dt equal to 0 to prove u bar is of constant magnitude. Again, over here I keep on stressing that point, that you can write it as simply as u bar, or you can write it as u bar t. It really is just a notation. Okay, it depends on you. Okay, the proof will go like this. Okay, so substituting this one in equation 1, writing this one in a square box. Okay, so u dot du dt equal to 0. So substituting it over here, you will be having u du dt equal to 0. So this is what we are having. Okay, so over here what we can do, we can have u bar is equal to 0, or ddt u bar equal to 0. So magnitude of a vector is 0. So the only possibility is that u is a 0 vector, or ddt of this one is 0. So u bar is equal to constant vector. So from both the cases, whether it's this or this, it will be constant, because if it is also 0, 0 is still a constant, right? So for both the cases, this or this one, we will be having u bar is a constant. U bar is constant. Okay, so sorry. Okay, so sorry, over here also it should be this one. Okay, so whether it's this one or this one, we will always have that magnitude is always a constant. Okay, because 0 it is still a constant. Okay, so this is what we have. Okay, so this also proves theorem 2. Okay, they are very easy theorems. You just have to remember the starting point. Okay, as a note, if u is any function of t, okay, so u bar, u cap, it will also be a function of t, but it will be the it will always be of magnitude 1. Okay, so what I'm saying, u bar is a function of t. This one, it will be of constant magnitude 1. So the dot product of this one, it will be 0. It will be 0 since u bar is of constant magnitude 1. Okay, so the magnitude of this vector, because it is a unit vector, it's always 1. So that's why if you take the dot product with d u cap dt, it will be 0 by theorem 2. Okay, so keep this in mind. Okay, we are going to use this one in the next theorem 3. Theorem 3, it says that u bar t is of constant direction if and only if u cross du dt equal 0. Okay, so now over here it is a 0 vector because this left hand side is a vector. Okay, so let's try to do it. Okay, so over here we need something that relates with direction. So what I can write, you have to remember this line. because if you forget this line, then it will be very difficult for you to proceed. Okay, so u vector, it can be written as, okay, you can write it like this. Okay, magnitude u into u cap. Okay, because if you remember, u cap, it can be written as u divided by magnitude u, right? So that is how I get this one. So what we will do, we will differentiate both sides with respect to the ddt equal ddt of this one. So what I can do, okay, this one, it is a scalar, but it is not constant, okay, because it doesn't have constant magnitude. Okay, so you cannot take it outside. So if you need to differentiate this one, you will have to use the product rule. Notice also that in between we are not having a cross or a dot because it is a scalar and a vector. So the left hand side remains as it is. And over here you are having, okay, it will be magnitude u, the u cap dt plus, okay, d u dt. This one is an arrow, so you'll be having something like this. Okay, now what we will do, we will just take the cross product with u from the left hand side. Okay, take the cross product with u, you will be having something like this. Okay, this one, it is a scalar, you can take it outside, you can take it to the front. And also over here you will be having du dt. Again, this one, it is a scalar because it is the derivative of a magnitude, which is a scalar. You can take it outside, you can have something like this. So we can also do this. Okay, so magnitude u, we can write it as it is. Now this one, u, again we can write it as magnitude u cap plus, now u times this, okay, the cross product, they are in the same direction, okay, they are parallel. If they are parallel vectors, so the cross product, it will be equal to 0, okay, plus 0. Okay, since u cap, if you have to write reason, are in the same direction. Okay, so you will be having this. You'll be having magnitude u squared du dt. Okay, so this is what we are having, and name this one as equation 1. Okay, now we will prove that u bar t be of constant direction if u bar t is of constant direction. So what can we have? So we will have ddt of the unit vector, okay, because we are concerned with the direction. So this one will be, okay, maybe I will write it. So this means that this one is constant. If this one is constant, so ddt u cap is equal to 0 bar. Okay, so substitute this one in 1. Substituting in 1, we will be having, okay, so this one will be 0. So the left hand side will be 0. Okay, 0 vector. Because everything is a vector, this one is also a 0 vector. Okay, so we will get this. Now let us do the converse. The converse will be, let this one be 0. We need to prove that the direction is constant. Okay, so we'll keep that in mind. Okay, so this is what we are having from 1. Okay, so if this one is 0, so the left hand side will also be 0. We are having this. Okay, so the left hand side was something like this. Okay, so now what we can do? Okay, so over here you can see that this one is a scalar. Okay, we can divide both sides by this scalar. Okay, we can do that. We can divide both sides by the scalar provided this one is not 0, because you cannot divide by 0. Okay, so what I will write, call 0 bar over here, provided this quantity is unequal to 0. Okay, so this quantity is unequal to 0. Okay, so now what can we have? Okay, so from over here, what we can write is, if you remember, so this one we can have that this one is equal to 0, or du dt equal to 0, or we can also have that the angle between, if this one is 0, so we will be having this one. If this one is 0, again we will be having this one. Or if the angle in between them is 0, so, or what I can write, u bar parallel du dt. If they are also parallel, so the angle will be 0, so the cross product will still be a 0 vector. Okay, this whole thing should be written as, okay, equation, okay, sorry, okay, okay, so over here what I can also conclude, so this magnitude, it won't be equal to 0, because, okay, from over here, equal to 0, or u bar parallel du dt. Okay, since the magnitude, since unequal to 0. Okay, so this is what we are having, but also this whole thing we can write it as star. Okay, maybe equation A or expression A. It is not an equation, so it will be expression A. Okay, so this is what we will write. But also, if you remember the note that I've written before this theorem, but also this one, it will be equal to 0, because it's of constant magnitude. Constant magnitude 1. Okay, what I've written in the note was this. So what can we have? So we can have u bar equal to 0, du dt equal to 0, or u cap perpendicular. If they are perpendicular, that is, the angle in between is 90 degree, therefore this dot product will also be 0. So this is what we are having, but again, this one is impossible. Okay, so this is what we are having from A and from B. Okay, from A and B. Okay, these two things, they happen at the same time. Okay, so this means that parallel and perpendicular cannot happen. Okay, two lines, they cannot be parallel to one another because these are vectors. Okay, everything are vectors. Vectors, they are represented as line segments. The lines cannot be parallel and perpendicular at the same time. Okay, so these two cases are ruled out. Okay, they cannot be happening at the same time. So the only possibility will be these cases. Okay, but U bar cannot be parallel and perpendicular to du dt at the same time. So from A and B, we must have, so sorry, this one is du dt. Du dt equal to 0, which gives that U bar is of constant direction. Okay, U bar is constant, which ultimately imply that this vector has constant direction. Okay, but this one we did, remember that line we have provided magnitude U is unequal to 0. But what happens if magnitude is equal to 0? Okay, this is also part of the theorem, but you can write it maybe in a square box. Note, if magnitude U is equal to 0, this is still part of the answer. If magnitude U equal to 0, then U will also be 0 vector. Hence, okay, maybe I will write it like this. If magnitude U is equal to 0, so U, it will be a 0 vector. So it will have a constant direction. Okay. Okay, so direction is undefined. Okay, so this is also part of the theorem. Okay, so you can end the answer up to over here. So we have done it. If U has constant direction, we will be having U cross du dt equal to 0 bar. And if U cross du dt equals 0 bar, then we will be having that U has constant direction. Okay, so these are the three theorems that we are doing, and they are very important, as you will see when we are doing some exercises based on these theorems. Until next time.